So after we learn about the basics of equilibrium constants and the equilibrium expression and the reaction, we are going to see how these knowledge can be applied in some specific examples. Now, before we go into the examples, I want to show you something. I want to show you how a strong acid dissociates. So here we see HCl, hydrochloric acid, dissociating into hydrogen ions and chlorine ions. And we see a single arrow because for hydrochloric acid, we assume it is going to be completely dissociating into ions. And of course, it is going to be almost completely dissociated into ions, but we're going to assume this completely dissociating into ions. So let's say we have 0.5 molar of the HCl. That is before dissociating. And during the process of dissociation, all the 0.5 molar is going to disappear because they are going to separate. The HCl is going to disintegrate. They dissociate and making hydrogen ions and chlorine ions. And they're going to have the same concentration as the hydrochloric acid because we have 0.5 molar of the HCl, and H and Cl, they break apart. So you should have the same concentration of the hydrogen ion and the same concentration of the chlorine ion. So I hope this is a very familiar example that we have learned so far. And now we are going to look at the other example, which is what we would talk about intensively. So here is a chemical equation for the dissociation of acetic acid. Now, the major difference in this chemical equation and the previous chemical equation is the use of arrow. In here, we use a double arrow because we knew that it's a weak acid. It is not going to be completely dissociated into ions. So we have to use a double arrow to show that it is an equilibrium process. Now, let's say we have the same concentration, 0.5 molar. And we understand that it is going to dissociate, but it is only going to dissociate slightly. Now, after the dissociation, what is going to happen? What would be the concentration of all these three chemicals? We don't know. We don't know. But what we know is that at the very beginning, before the acid is being dissociated into ions, this is definitely not at equilibrium. Because when we talk about equilibrium, the definition of equilibrium, we understood that it is when the forward reaction is, the rate of the forward reaction is the same as the rate of the backward reaction. And now we have some reactants right here, and that is okay to go forward. But on the other hand, on the product side, since it is before dissociation, we have nothing. We have no ions in the product side. And if we don't have any product, how do they go backward to make the acetic acid? Impossible. So we know that it is not at equilibrium yet. Therefore, it must undergo some changes. Okay? There must be some changes to achieve equilibrium. So with this concept, we develop a tool to help out calculating what is the concentration at the very end. And this is called the ICE table. The ICE table stands for, the I stands for the initial concentration, and the C stands for the change of the concentration, and E stands for the equilibrium concentration. So we would like to see how things are changing, how the concentration, how the concentration of the chemicals are changing in order to achieve equilibrium. This is how we develop this tool, this table, to help us to keep track of the concentration. So we understand that it is a weak acid. We understand that it's going to dissociate slightly. But we don't know how many of the molecules are going to dissociate into ions. We do not know. So what we do is that we are going to use an unknown, X, to represent the amount of the molecules dissociating into ions. And since we have this amount dissociating, we should have the same concentration of the ions for each ion to form after dissociation. So that's a change, and we would like to see what is the equilibrium expression, equilibrium concentration. We would like to see what is remaining at the end. So this will be the concentration of the acetic acid. And these two will be the concentrations of the ions.